Oh, oh yeah. John was my PhD student at USC. Yeah. All right. Let's see. The title says it, Technology Readiness. The BWB is a different kind of an airplane. We could say derivative of the B-2, but it a lot of challenges. To set the stage, first slide, please. Note the date, 1993. We had a NASA contract that to look at it. The thing on the left was our first try in 1989 at a conference at NASA Langley, fostered by the shy Dennis Bushnell. And could there be a different configuration to a DC-8 or a 707? And we started out with that thing on the right. Why? A subsonic transport has its pressure vessel go to the design load every flight. But the wing doesn't go to its design load of 2.5 Gs every flight. So the pressure vessel has to work real hard, and the best way to take pressure loads is in hoop tension. And you can maintain hoop tension by putting circles together, and the floor becomes a tension member and so on. And you get something like that on the right. But that's not very streamlined. So we'll just put an elliptic shape around it, and then it'll be streamlined. Now we have a pressure vessel within a pressure vessel. What could go wrong? So we abandoned this. You'd have to make the outer shell be able to take the pressure in case the inner stuff leaked. So that was bad idea number one. So we moved on. Next slide, please. And this is a cartoon that dates way back. We have the configuration of a typical double-deck subsonic transport. And the early concept of the BWB, where you see the one on the left has got the circular sections that'll take the loads very nicely. One on the right has, in essence, a flat-sided pressure vessel. And in that case, you have to take the loads in bending. Every flight, you go to the ultimate load, the design load. It also shows that fuselages don't carry lift real well. You see the dimple. The blue is lift, and the red is weight or mass. And you want those equal. And so a fuselage doesn't carry that load very well. The other thing on the blended wing, notice that the weight is distributed uniformly across most of the span. Those two big spikes outboard of the center body, we call it the armpit of the wing, but there's a lot of fuel volume there and enables the BWB to be a good tanker. And notice also that we carry the load all the way out to the tip and up the winglet. The other thing about this figure is, conventional airplane, you've got two big things at 90 degrees to one another, and you've got to pass all the loads through those. Whereas on a blended wing, you're lined up. So it's a very simple structure. And it's just a big wing, in essence. And this has enabled a lot of the performance gains that we've been able to show. Next. Okay, now this is 2001, and this airplane was an early, well, at the time we thought it was the latest thing, but we worked real hard on this one, and the 450 stands for 450 passengers, and we did a lot of analysis on design of it and the structure. So we chose it to use for the X-48. Now I'll go to the next slide. Oh, got to complain with the other guy's airplane. There is an A380 and a BWB of the same passenger capacity. I suggest painting Goodyear on the side of the A380. Next slide. So what are the real challenges? First of all, a BWB is a nonlinear airplane design. By nonlinear, you poke on it anywhere and stuff changes everywhere, it seems. A tube and wing airplane, which I use in my airplane design classes at both MIT and UCI, is simple. The fuselage has one design parameter, its diameter. The wing has two, sweep and aspect ratio. And then somebody like Norm Princeton puts a big tail on it. So I moved down to the next thing is robust flight mechanics of a tailless airplane. There are a lot of tailless airplanes around, but still, we wanted it to fly just as well as a C-17 or an A330 or whatever. Okay. And those airplanes have some funny traits. They, tailless airplanes, often you get into if they stall, they'll depart in a pitch tumble, either direction. And you probably don't want to schedule meal service then. So the flight mechanics was a big challenge. And then the other thing hey, we're going with a flat-sided pressure vessel. Well, you can make one, yeah, but it'll be heavy. So what we took on was those bottom two things, getting the flight mechanics so it was robust and it flew like a regular airplane, and it'd be lightweight. Next. And here we have, hey, the B-2 exists. They don't stall the B-2. It stops way short of CL max. And, well, you don't have to make money with a B-2. So you can carry around the extra wing for margin, and it's not that big a deal. But we wanted the BWB to be able to sail over the top of CL max there and still act like a normal airplane. The other thing that goes on is, you see in the lower right, one of the inboard elevons. They're the size of your bedroom. And with the case of a tailless airplane, the bandwidth of the control surfaces is pretty high, 80 degrees a second. And you're waving a bedroom floor at that rate. So that's a challenge. Next. All right. The figure on the left is in the NASA spin tunnel. Note that the airflow in this tunnel is vertical. And they throw the model out a window, literally, and see if it spins or not. The YB-49 spun. That's a BWB on the right, and it spun. Uh-oh. And I was talking with the late Dwayne McBrewer and Irv Ashkenas. You flight mechanicers have probably heard of them. And Dwayne said that the inertias were wrong on the models, and that's why they spun, or pitch tumbled, or both. And what about the inertias? What are the two sources of a force on an airplane? Aerodynamics and inertia. And when we were doing an 8.5% scale model, the X-48, and it turns out the inertia scale with the fifth power of the length scale. So now if you say that, to build this, I guess we'll go to the next slide. there's the airplane, 21-foot span, 500 pounds, but it's still a big airplane. But to meet the inertias of the full-size one, we almost had to build the outer wings out of Kleenex. And so it was a real challenge to get the inertias close, to have a dynamically scaled airplane. And the other thing is, the entire airplane was fabricated at Cranfield Aerospace in the UK, and did a lot of commuting on the 5:30 British Airways flight to London. But they did an exceptional job of building the airplane, built 2 of them. Next slide. A lot of stuff inside. I won't go, hey, I'll read all those things to you. No. A lot of stuff, but note that the outer wings are barren. It's to keep the inertias under control. Next slide. Another feature with working with NASA, and I'll say it probably more than once, this project was 50-50, Boeing and NASA, totally. And technically, we each paid our own way, in essence, but technically, NASA was right in there solving the problems alongside of ourselves. Here we are in the 30 by 60 tunnel. That's the full airplane, the X-48. And we were able to go in there and measure stability derivatives in hinge moments, which CFD isn't able to do. Right, John? And also calibrate the air data system. To be able to go in a wind tunnel with, in essence, your full-scale airplane was special. And there are 250 hours, and we knew everything we needed to know about the airplane. Next slide. There is the flight control station in a hangar out at NASA Armstrong. I got to keep saying that. At any rate, that's a small trailer. It was supposed to be able to go out and be just out in the desert, but we had, NASA provided, an air-conditioned hangar. And we lived in it for 8 years, I think, or more. But notice it's a small trailer. That's so only the pilot and a flight engineer and the guy to push the red button just in case. They're the only people that could be in there. And so it was flown from there. Next slide. Mike Sizu, a MIT graduate and a Boeing test pilot, is there in the pilot seat. And right in front of him, he's looking out of the video camera that's in the nose of the airplane. To the right is a GPS plot and so on. To his left is the red button guy, and to the right is the flight test engineer. My student, John Vasberg, virtually made this whole thing work every day. Next. Well, there's more stuff on there. Notice it points triple JetCat 200 engines. Those are model airplane engines. 55 pounds of thrust each, as I recall. But they were free. $3,500 a piece. Well, it isn't free. It is if you're going out to buy jet engines. And notice those probes on the front. Those are air data probes. They're just pedostatic and alpha and beta vanes. Out the back is a boom, and that's to, if we do abort the flight, we've got a drogue chute, and we don't want it to entangle. So the drogue chute comes out of the back of that, and the airplane, we had a complex system, I won't go into it, to try and save the airplane on abort. But when that drogue chute comes out, the airplane winds up going straight down at 90 knots. And then we had a parachute that comes out of the top and so on. We never had had to do that. But this is 2007. And the picture without the logos was in Time magazine as the second best invention of, 2007. Anybody know? Excuse me, the first? Nope. So we were second. Oh well. Okay, next slide. Here's the first flight.
Skyway 48. Skyway 48, over, sir. 48 in position. Lake Bed runway 23, request clearance for takeoff. Skyway 40, roger, main base wind GT0, SSE 40 airborne.
We're in a pickup truck next to it. And Norm Princeton is holding the video camera out the window. This is NASA video now.
Skyway 48, airborne. The practice, I'll do a left turn for area orientation, but the real one will be right. There should be no trouble at all. And for card Lima 6, we are at high key. Skyway 48, practice high key. Throttle on.
T-34
Throttle on. Speed and power's coming
chase
back.
plane.
Verify tape mismatch.
Yes.
Check control.
Control is correct.
Throttle off.
Throttle disengage with the throttle button.
Full doublet when able.
Doublet in 3, 2,
Doublet and roll.
complete.
Doublet when able.
Doublet in 3, 2. See sweep complete. I'm going to come to the right, Frank, and we are at Joker fuel.
Okay, well clear, and I'll stay on your left side.
Right.
Confirm frequency sweep, we're good.
Okay.
And after the turn, we'll roll in the yaw, and I think that's going to be it. We're going to have to go to the descent card. Lima 14 will be the next card after completion of Lima 8. Lima 14.
Out here. We're passing Meeper this time.
Okay, we're Meeper, and pilot perform brake check.
Good.
P-15, approach and land. feet, 5-5. Feet. Good laser. 5-3.
There's a shot of this from the chase plane.
25. 20.
And Carla,
15,
the lady photograph or videoing
5.
it, lets out a sigh.
25.
This is the one.
20. 15. 10. 5. And you can resolve fire relief without the vehicle. That's very, very good.
Yes, sir.
Time 0912.
Hold on the brake.
Okay, next, Norm. There we are on the lake bed. Norm is furthest in front of the truck. Gary Cosentino, a NASA guy that held our hand through this whole thing, is right next to the airplane. And I'm standing in front of the truck. Okay, next. So what did we have? It's a different airplane. It's got an allocator that can, you don't just pull back and an elevator moves. It decides what it's gonna move. And all the practice had to come via the flight simulator. So the test pilot, first time the airplane flew, he wasn't in it. Well, he never in it, but just via the simulator. And right afterwards, it was Norm Howell was the first pilot, and I said, Norm, how did it compare with the simulator? He said they're identical. And and he said he liked the way it flew, which was impressive. You know, I got in this business as a model airplane builder way back. My first radio control airplane had vacuum tubes. But here I had the most bitchin' model airplane, and I never got to fly it. They let me fly the simulator. Okay, next. This is, we spent a lot of time flight testing, and those are CL versus alpha curves, and CM versus alpha curves. And the blue are the clean wing with no slats, so it stalls early. And then the red is with the slats, and the slats didn't automatically come out. We had two leading edges, one which was a slat and the other which was a normal leading edge. So on the right is a plot of CM versus alpha. This is how we established the maximums. And on the red, you'll notice that we set the stall speed, or the limiter speed, where the pitching moment changes sign. On the red, we could go, and if you notice the pitching moment just going up dramatically there, that's because the outer wing is stalled. It's pitch up. Now, with the slats, the outer wing doesn't really do that, so we are able to go all the way up to the point you see there. But this is how we set the limiter values that you'll get to see exercised. Next. Okay, these flights, the pilot just slams the rudder.
Recover?
And recovering.
17.05 max.
Okay, good point. Let's do 4 Bravo in opposite direction.
Okay, slight right turn and then a left rudder. And stable.
You're clear.
Rudder on 3.
Recover.
Just goes to the stop.
17.31 max.
See the airplane come out the other side?
In 3. Recovering.
17.49 max.
There will be a left rudder step. Stabilizing. Bank. Ready?
Casey, still ready?
Ready. In 3.
Watch the left wing show a big red flash there. That is the drag rudder open.
17.49 max.
9 complete.
Maneuvering in 3.
This is out the pilot's view, out the nose cabin.
Recover.
Recovering.
17.49 max.
Next maneuver will be a left rudder step. Stabilizing. Right bank. Pilot ready?
Casey, still ready?
Ready. Maneuvering in 3. Now. Recovering.
17.49 max.
Pilot would hold
Even
those
nine complete.
controls for 2 or 3 seconds, just at the stop. Now these are angle of attack limiters, flights, And the
Coming
first
right
one is
in
slats
3.
extended. And you go into a 60-degree bank first to pull 2 Gs, just for scaling.
Recover.
And 19.95 max.
Okay, I think I'd like to do 5 alpha again.
Okay, we'll be rolling in 3.
Right, 60-degree bank. And then he pulls. And it breaks
Knock it
over
out.
the top.
22.24.
That's the north base runway down there.
Okay, we'll be rolling in 3.
Knock it off.
22.24.
Oh, you're just looking at blue sky once it's got its nose pointed up.
Maneuvering in 3.
One where I think it looks like a falling leaf.
.37 max.
Maneuvering in
TC
3.
ready.
This is from the ground video. Notice that the airplane turns inside of the T-34, same bank, and the T-34 couldn't stay with it.
Cover.
10.37 max.
Pi ready, maneuvering in 3.
F2 ready.
TC's ready. 5 Bravo, 95 knots, fast rate.
And the 60-degree bank, but this is from, we'll call it the pilot's seat.
Cover.
10.37 max.
Just run Bravo, 5 Bravo complete. Okay, I don't see a reason to repeat that run. I think we got data on that one.
See the moon go by?
Yeah.
We didn't go there, but. Okay, so very successful. The first part of the program, we did 80 flights. Those were Boeing flights, and then we did another 12 flights for NASA, flight mechanics people. And so we wound up with the X-48B having 92 flights, single string, and it worked remarkably well. And hey, some technical papers came out of it too. Okay, next slide. Next, we looked at making a quieter airplane. I've been dragged kicking and screaming into this one because I like the verticals on the wingtips. But at any rate, there it is, and it's the direction we're headed now. And we went to 2 bigger engines, or higher thrust engines, and this is called the X-48C. And it's got Norm Prinson's signature on it. The tails are bigger. Okay, next. We tested it also in the 30 by 60 tunnel. And incidentally, this was the last time the 30 by 60 tunnel was used. I threatened to pull a Tiananmen Square thing in front of the bulldozer that tore down the tunnel, and Faye said, please don't. But we went over, again, all the stuff for the X-48C, and then another test using another model in the Langley 12-foot to get a A to B comparison of the rudder effectiveness primarily of the B versus the C. And they were damn close. Okay, back to the winglet rudders. No. There is the X-48C in flight, and its last flight was on April 9th in 2013. And we got all of the data we wanted out of it. Okay, next. So where were we? We had a total of 122 flights for the whole project. Single string. I think that was a record at Armstrong. And so what's happening now? Well, the X-48C is in the museum at the Air Force Museum at Edwards. And the X-48, the other one is packed up, but they're ready to fly again. I was just talking to Israel Wignansky at lunch today about some control effectors that we could test on the X-48C. Norman is pretty excited about that. So we haven't given up. Those airplanes are still flyable. Next. This is the other problem. This is the structures problem. And if you look, there's a BWB. Well, again, this is our flat-sided pressure vessel. And normally, the skin of an airplane just takes NX and NY. But if you're pressurizing it, you have NZ load. So we needed a structural concept to do this. Next. There it is. Pultruded rod, stitched, efficient, unitary structure, Precious. This is the brainchild of Alex Felicki. To me, it's just a tooling concept, but it's dry preform and it's stitched, and then a bag is thrown over the top of it and resin is drawn in. But when you stitch it, as opposed to pre-preg, where you've got just layers of pre-preg tape, this is way more isotropic. And this is an ingenious way of tooling. And the next slide shows what happens when you do that. That's one piece. There are no rivets, there are no brackets, nothing's bolted together. It's one monolithic piece. And so we built a center box. Next slide. There it is. We wanted to build a full scale, but the Colts test facility at Langley would only hold 80% scale. And you see where it comes out of the BWB. And that was an impressive structure. And there's some cutaway on that. But well, will it work? Next slide. There's a better look at it. There's Alex standing in it, in the upper bay. And down below, Jaime Barrera is right there. And those two people were special in getting this thing done. So what are we going to do with it? Next. It wouldn't fit in the C-17. So we used the Guppy. And there it is. And not that long ago, the Guppy flew back to Langley. December last year. There it is, departing Long Beach. Next. And this Colts thing is the meanest thing to torture structure that you could imagine. Basically, it grabs each end of that center box and loads it with aerodynamic loads. And the maximum aerodynamic loads. And in addition, it's pressurized. And what we had was the critical design conditions, 2.5 Gs plus 1 pressure. But we tested way beyond that. Next. I'm sorry, let's go back to that. At the design, those are the design values. It didn't break. And we even went to the ultimate load and didn't break. So, next slide, we went and hit it with a hammer. And then in the lower right corner, that's a 2-foot long slice, 1 inch wide, trying to hurt the thing. Well, the only thing it wouldn't do was hold pressure. But when we loaded it up, the next slide, I think has a summary of it. There. We had the 5 load cases where, incidentally, on these 2.5 G things, we put twice the pressure load on it. And those 5 top test cases, the thing was happy. Enter the Sawzall and cut frames. And still in the test fixture, a requirement, FAA, FAR, is that you go to, with a damaged structure, you get to 71% of design limit load. With the broken structure, it went to 151 design limit load. And it acted like metal because we've got, with metal structures, we still use the 2-bay crack rule and all that. And the thing acted like metal. Here's the big answer. Minimum gauge. The skin on that thing is 52 thousandths. That's a little more than a 16th, in other words. I mean, a little less than a 16th of an inch. That's the skin. And we can use that everywhere. So, not only did it not break and exceed the numbers, it's light. So, next slide. Another thing going on that was just presented here, the ARA thing. And this is a different airplane, the more modern BWB. There are several talks on it going on now. But it was tested with flow-through nacelles, ejector-powered nacelles, and turbine, TPSs, turbine power simulators. We were looking at the effects on the control surface of the exhaust, and you can see the white plume there. And again, tried to make it not work. And it'd take too long to go through all the things, but it was a smashing success. Next. So, where are we? The X-48 stuff said we've got a robust airplane. Alex's structure works. We can build the airplane and have a pressurized center body. And it exceeded, as I say, all the limits. And finally, what's the next step? Well, I showed you the guppy there. We had to use the guppy because that thing wouldn't fit in a C-17. Going over the ramp, you couldn't put that box in. But with a BWB, if we want to have airdrop, we have a clamshell door in the back. We worked with the Air Force on this. And so you can airdrop from the airplane, and you can trim it. Normally, if you put that, just the lower ramp down, the airplane would pitch down. But we raise the upper ramp too, and it gives us more clearance for the cargo. And we did spend quite a bit of time on the design of that and weighing it, and that works. So In the meantime, we want to do a flight demonstrator, and you've probably heard that. And we built a pick your size array of BWB demonstrator candidates, and these aren't just cartoons. We sized them and weighed them, and any of them could be real airplanes. So let's see. The next slide is controversial. You know, you acknowledge, and you make about everybody isotropically unhappy. Why is he there and why aren't I? Or why'd you put me on there? At any rate, we took a shot. And three key people on that thing are Norman Princeton, Alex Felicki, excuse me, and Fay Collier. Fay fell on his sword several times to keep this thing going. The airplanes were built by Cranfield Aerospace, and we could fill pages with acknowledgments. But that's a try at it. Next slide. That's it.
Well, Bob, thank you very much. It turns out that we've got a little bit of time for questions, so if anyone would like to ask Bob a question, we'd invite you to step to a mic if we have one. All right, thank you. Any questions? Oh, surely.
They believed it.
There's one back there. Come on.
Probably right around 1. Now, bear in mind, we base CL on the total planform area of the airplane. Put in more bays. And you can, just looking at that figure, you add bays, you spread the airplane laterally, and you gain wing area and wingspan with each different size. So it works very well doing that.
Yes, sir.
You mean percent? 0-ish? Actually, we don't want a lot of static margin because, again, it's a tailless airplane, and we got a flight control system, so we weren't. Norman, you're back there. What was the static margin? Give me a number. Yeah. Makes it easier to fly. If it were up to me tomorrow, but all we can do is say, hey, you can build one of these. And I think you can now. I think it would be higher risk than a tube and wing airplane, but I don't think there are any showstoppers. Yeah. We looked at that, and in the passenger version, you have a door in the leading edge for each aisle, and out the rear spar in each aisle. So you've got a fore and aft door for each one, and then there are cross aisles. We ran a test at Cranfield. We used the A380 test fixture, and we had a 4 or 5 bay BWB mock-up in there, full scale. And we had Cranfield people acting as cabin attendants. And one of them was like a drill sergeant. but screaming, "Get out, get out." We tested for a couple of weeks. We'd bring in people from Newport Pagnell in the UK, pay them 40 pounds to try and run out of the airplane. And there was a lady, a Professor Helen Muir at Cranfield, who was the authority on air rage and psychology and all that. And she deemed it the most aggressive airplane she had dealt with.
Over here?
Oh, yeah. Yeah, we've got very detailed weight estimates, and we've got aero performance, worked thoroughly, and we've worked, it's been worked both in, I'll say, Long Beach and in Seattle with different goals, but agreed on the numbers. And the airplane typically, if you're doing an A-B shootout of a BWB versus a tube and wing for the same application, military transport or whatever, the BWB typically shows a 15% lower fuel burn.
Yes, sir.
What parameter are you talking about? Yeah? No? No, you've got, as I say, it's fly-by-wire. I'm not following you on that, I'm sorry. Normal FAR requirements. Yeah.
Others? Yes, sir.
Alex? They wanted to know if the structure deformed a lot under pressure.
All right, one more if we've got one. Yes, sir.
Cost. That's the same thing we did to have the slat, two removable leading edges. And those landing gear were in the position where the actual landing gear would be. My son, who's a mountain bike downhill racer, got us the brakes for the main gear. And one of my USC students from way back, named Joe Bach, I lost track of him, and then I ran into him at a meeting. He was at USC, he was a linebacker. And I could recognize him right away because the guy doesn't have a neck. And, Joe, what have you been doing? Well, I played for the Steelers for 4 years. And then he formed a company called Aerotelemetry. It's in Huntington Beach. And he built the nose gear for the airplane. In addition, he built all the models for the movie The Aviator. Got to plug the students.
All right, well, let's give Bob a big round of applause for his.
And I want to thank both NASA and Boeing to be able to do this.